Welcome back. In the last video, last few videos, we proved the main theorem of Galois theory, and we learned, for example, how to prove fundamental theorem of algebra using the main theorem of Galois theory. So in this video and one or two videos after this, we are going to do some problems. So before we proceed further and see more applications of the main theorem, it's good to learn how to apply so far whatever we learned so far and solve some exercises. So let me start with some observations that I made in the past, but I want to record them concretely so that you have a record of them and we discuss all the missing details. So first problem is, let K over F be an extension of finite fields. Okay, so then K over F is Galois, that is the first statement, and moreover the Galois group K over F is cyclic. Okay, so let me give you a definition here before we proceed with the solution. A finite extension. So just a word about terminology. So finite extension always refers to an extension of fields that is a finite extension. Here I am not, when I say a finite extension, I am not asserting anything about whether K and F are finite fields. That's a general statement. Here I am saying K over F is an extension of finite fields. That means K and F are finite fields. So there is a big difference between this. So a finite extension K over F is called cyclic if K over F is Galois, so it has to be Galois first, and the Galois group is cyclic. Okay, so a cyclic extension is a short form for a Galois extension whose Galois group is cyclic. So examples of such things are, for example, Q root 2 over Q is cyclic, right, because its Galois group is Z mod 2Z. On the other hand, Q adjoint fourth root of 2 Q is not cyclic. So this is because it's not even Galois, right? So it's not a Galois extension, so it cannot be cyclic. Only after you determine that it is a Galois extension, you ask for its Galois group. On the other hand, if you take Q adjoint omega cube root of 2, omega comma cube root of 2 over Q, this is Galois, but the Galois group is S3, so it is not cyclic. Okay. So the assertion of this problem is any extension of finite fields is cyclic. So that is what the problem is asking you to show. So if you have two finite fields, one containing the other, it is a Galois extension and its Galois group is cyclic. In other words, it's a cyclic extension. Okay, let me prove this. This is something we have done before. Let's say characteristic of K is P. So this of course will be characteristic of F also. If you have field extension, both will be same characteristic. So you have K over F, but this both live over the prime field. So we know, so this I will assert without proof. K over Fp is Galois and Galois group of K over Fp is isomorphic to Z mod Rz. Sorry, is a cyclic group. Let me simply say that is a cyclic group. So K over Fp is a cyclic extension, right? So this is Galois, and that is because recall that the Frobenius map generates the Galois group. In proving this, in fact, we also proved that it is Galois extension because the Frobenius map will have the right order. So that order is the degree of this field extension. Now by the main theorem, this is not main theorem. I mean, K over F is Galois is actually not the main theorem. That is just a standard fact about Galois extensions because they are supposed to be normal and separable. So this is Galois what main theorem says is that Galois K over F okay, this is even not the main statement of the main theorem, but I am putting every statement about Galois groups and subgroups under the heading of main theorem. So, it implies that this is a subgroup, but this is cyclic. So, this implies this is cyclic. A subgroup of a cyclic group is cyclic. So, we are done. So, this K over Fp is a cyclic extension. So, K over F is a cyclic extension. So, that is the solution for the first problem. Okay, so this and first problem and now the second problem are not new to you. I have sort of mentioned them before, but I wanted to explicitly talk about them once more. So, show that a normal extension need not be Galois. So, remember Galois equals normal plus separable, always finite. So, all extensions are finite for me. So, a finite extension is Galois if and only if it is normal and separable. But the point is, it is not enough that it is merely normal. In characteristic 0, of course, it is enough, but not in general. So, the argument here is you take, let us say Fp t. So, where p is a prime number, of course, and t is a variable. Okay. So, this is the field of rational functions in one variable over Fp. And let us consider the polynomial f of x in fx given by so I think I did p equal to 2 case, but more generally one can do this. Take x power p minus t. So, first claim is that f is irreducible over f. Okay. So, for p equal to 2, all you need to argue is that it has no roots, but for higher values of p, it is not enough to argue that it has no roots, but one can argue that it is not separable and it has only one root. So, actually what we will show is that, so let us take the fixed field, the splitting field. So, f, let me remind you, is Fp round bracket t. So, let us take the splitting field of f over t. Then f has only one root in K. So, the reason is, so let alpha be a root of f. In K. So, let alpha be a root of f in K. Because K is a splitting field, f will have a root. So, let pick one of them called alpha. So, we have alpha power p equals t. So, now I claim that there can't be any other root. So let us take the polynomial x minus alpha. So, what is how does f factor in kt, kx. So, that is what I am saying, that is what I want to understand. So, I claim that we have f of x equals x minus alpha power t p. Yeah. So, this is because x minus alpha power p, since characteristic is p, x minus alpha power p will be x minus p minus alpha power p, all the mixed terms will go away. So, this will be x power p minus t. Okay. So, alpha power p is t, right. So, this is true, and in a polynomial ring over a field, factorization is unique. So, this is of course fx. Okay. So, this must be the unique factorization of f in kx. Of course, this factorization is not available in capital Fx. So, this is only available in capital Kx. So this proves you in one shot that f is not separable and also that it is irreducible. So note that this also gives that f is irreducible over f. Okay, so this is because if it is not, it will have a factor and those factors must involve x minus alpha. So actually this requires a little bit of proof. So I am going to leave this as an exercise for you. And I want to get back to the main part of this problem, which of course is to show that K over F is not Galois. So, and for that I don't need F to be splitting field. So, F to be irreducible. So, this claim is in fact an exercise. So, I would rather, I mean I want to do other problems. So, I will skip this. So, I want to say that F is irreducible is a exercise for you, that is irrelevant to the problem that I am trying to consider. So, now because of this, so what is the conclusion of everything that we have done so far? K over F is normal because K is a splitting field of x power p minus t, right, and K over F is not separable because alpha is not separable over F. Okay. So, this is because the irreducible polynomial of alpha over fx over f rather by the claim is x power p minus t, and this is technically without proving the claim, all you can say is that irreducible polynomial is a divisor of this, but once you prove the claim you can show that this is the irreducible polynomial, and this of course I called f of x, and f of x does not have distinct roots in K. So, it is not separable, right. So, it is not separable because it does not have distinct roots, and you can actually make do without this claim, because all you need to know is that the polynomial has no roots in K, no roots in F, which of course is true statement, because there can't be a rational function whose pth power is a t. So, that we argued before when we talked about this in a previous video. So, this has no roots. So, the irreducible polynomial will be at least degree 2 and only root of this is alpha. So, it does not have distinct roots. The number of roots is strictly less than the degree. So, it does not have distinct roots. Irreducible polynomial does not have distinct roots. Even if irreducible polynomial is not this, it is a factor of this with degree at least 2. So, it does not have roots and hence it is not separable. So, K over F is not Galois. Okay. So, you can also see this by alternatively you can show non-Galois by there exists only one F automorphism of K, right, because any automorphism that fixes F, any F automorphism must send alpha to alpha, okay, because alpha is the only root of the irreducible polynomial of alpha. So, any automorphism must send alpha to alpha. So, the order of the Galois group is 1, which is strictly less than the degree is p. So, again equality here follows from the claim, which I have not proved, but even if you do not agree that the x power p minus t is irreducible, what you can definitely say is that k colon f is at least 2, even without the claim. We know k colon f is at least 2. So certainly we get a contradiction because we get non-galvanized because 1 is strictly less than 2. Since x power p minus t has no roots in f. Okay, so this has no roots in f, so this is at least 2. So the cardinality of the Galois group is strictly less than the degree, and hence it's not Galois. And finally, before I move on to the next problem, let me remark finally that claim is easy to prove. When p is 2, this is a degree 2 polynomial, and a degree 2 polynomial is irreducible if and only if it has no roots. So it has no roots is an easy statement, and that is enough to conclude irreducibility in p equal to 2. So you do have a normal extension, that's not Galois, by taking characteristic 2, but in general you can also do this, and without proving the claim also we have shown that it's a normal extension and it's not a Galois extension. But it's still nice to prove this claim and complete the picture and conclude that this is an equality, the degree is actually p. Okay, that I'll leave for you to do. Okay, so now let me continue and do some more examples. So the next problem, okay, so let's see what I want to do next. Yeah, so let's see the following problem. This also is something that came up before, but I'm trying to tie loose ends here and settle this. This is a nice statement, and this is something we will see more generally later. So suppose f is a field, and suppose characteristic of f is not 2. Okay, so f is any field, all we are assuming is that its characteristic is different from 2. Let k over f be a degree 2 extension. Then k over f is Galois, and k is in fact equal to f alpha, where alpha square is in f. So what we in words, basically what we say is that k can be obtained by adding a square root. So you take alpha square, that's in f, so you add a square root of that to get alpha, so k equal to f alpha. So this is a nice structured result for degree 2 extensions of fields which are not characteristic 2. Okay, so the proof is very simple here. So what we know is that its degree is 2, so we can assume that there is an element, we not assume, we do know that there is an element that we can take whose let's say beta is, okay, so let's say alpha is in k minus f. So that we know exists because k is different from f. So then we don't quite know that alpha will do the job for us because alpha square may not be in f, right? So we don't know yet that this particular alpha will do. But what we will do now is to exhibit some other element which does the job. So since k colon f is 2, there exists, the degree of fx is 2, where fx in capital Fx is the irreducible polynomial of alpha over capital F. So remember k equal to f alpha. So this implies degree of alpha over f is 2. That means its degree of its irreducible polynomial is 2. So let's write down what that is. So say fx equals x square plus bx plus c, where b and c are elements of the base field. So x square plus bx plus c. Now what are the roots of this, because of the quadratic formula which we had recalled earlier. Right? So these are the roots, and here is where the characteristic different from 2 hypothesis is used. Because you can't divide by 2 if the characteristic is 2. So roots are given by this is a statement that only holds in characteristic different from 2. So the roots are this. Okay, now let's take delta to be square root b square minus 4c. So this is called the discriminant, if you are familiar with this terminology, but that's irrelevant. So let's take this delta to be this. So I claim that k is f delta, okay, and delta square is f. So the proof, so this proves the part about k being generated by a square root of an element in f. So clearly delta square is b square minus 4c is in f. So this is okay. So but why is k equal to f delta? So this is also clear because k is here, f delta is of course here, because delta is in k, of course delta is in k because the roots are in k. So alpha is minus b plus b square minus 4ac by 2, or alpha is minus b square minus 4c by 2, right. So alpha is a root, so alpha is one of them. So if once alpha is in k, if alpha is in k, you can clearly rearrange terms to conclude that square root b square minus 4ac is in k. So f delta is in subfield of k, and this is a degree 2 extension. So this implies f delta is either k or f delta is equal to f. So if f delta is k is the statement. If f delta is equal to f, this implies delta is in f, but that means f has roots in f, right, because if this delta is in f, minus b is of course in f, so this whole term is in f. After dividing by 2, it's still in f. Similarly, this is in f, but this means f is not irreducible in f. So this is a contradiction. Correct? This is a contradiction because f is the irreducible polynomial of alpha. So that means f delta must be in k. Okay, so that proves this. And finally, the Galois is also clear because k over f is Galois because two things. K over f is normal because it is a splitting field, right? Because the roots of f are this minus b plus square root b square minus 4ac by 2 and minus b square minus 4ac by 2. There is no a, so this is c. So the point is, if this is alpha and alpha is in k, this means this is also in k. Okay, so this is a simple observation because b square minus 4ac is in k. So basically the roots are minus b plus delta by 2 minus b minus delta by 2. If delta is there, then both are there. So this is the splitting field, and f is separable because you can check because its derivative is okay. So this is non-zero. Okay, so we know that a non-separable irreducible polynomial must have degree derivative 0. So here again characteristic f not equal to 2 is used. Okay, so it is separable. So one can argue that if delta is separable, if alpha is separable, then f alpha is separable. So that's a general statement. So k of f is normal and separable. So k is separable. Okay, so basically this is there is a small little statement here. So this is an exercise which really is an exercise about so if alpha is separable over f, implies f alpha is separable. So all polynomials in alpha will continue to be separable. So this is an exercise about separable extensions, which I will not do for now, because that's not the point of this course. So using that, we know that it is Galois. Okay, so any degree 2 extension of a non-characteristic 2 field is Galois. Of course, that's false if you take characteristic 2 as this example shows. Okay, so this tells me that the third problem is solved. So any degree 2 extension is Galois and it is obtained by adding the square root. Okay, so let me do one more problem before we stop, and then we will continue with in the next video. I'll do some more problems. So this is next problem is very nice also. So the fourth problem says, let k over f be an arbitrary Galois extension with such that the Galois group, let's call that G, of the extension is isomorphic to S3. So S3 is always the symmetric group on 3 letters. So order 3 group, order 6 group. So G is isomorphic to that. Then show that K is the splitting field of an irreducible cubic polynomial over capital F. So this is a nice statement. So in general, every Galois extension of whose Galois group is S3 must be the splitting field of an irreducible cubic polynomial. This is a nice statement. Okay, so let's see why this is the case. Okay, so because G is isomorphic to S3, so first point is there exists a subgroup H of G of order 2 and H is not normal in G. Okay, this is the feature of S3. Of course, any group of order 6 will have a subgroup of order 2. That is not, for that you don't need S3, but you need S3 to conclude that it's not normal in G, right? Because S3 will have degree 2 elements. So that any degree 2 element you take and you take the group generated by that, that will be a group of order 2 and it's not normal. So this is a property of S3. So this is where S3 will be readed. Okay, so let's call that H. So now we have K. The fixed field of this, let's call that KH, and living underneath all that is F. So now the main theorem of the Galois theory says, here we do need the main theorem, the full force of the main theorem in this problem. What does main theorem say? First of all, it says that degree of this extension is 2 because the order of H is 2. And degree of this extension is 3 because index of H is 3 and this whole thing is degree 6. But more importantly, the main theorem says that is not Galois, right? It is not Galois because H is not normal. Okay, since H is not normal, so it's not Galois. Okay, so now if it is, but we do know that since it is degree 3, we know k power h is f alpha for any alpha in kh, not in f. So take any alpha that's, because these are not equal as fields, there is an alpha in kh that's not equal to, that's not in f. So then f alpha is an intermediate field, it cannot be equal to f, but this is a prime degree extension, so it must be equal to k f alpha. F alpha must be equal to kh. So now this means we have not yet used the non-Galois-ness of kh over f. We are only using the fact that 3 is prime. So let fx in capital Fx be the irreducible polynomial of alpha over f. Now since f alpha colon f is 3, degree of f is 3, right, because degree of f alpha over f is simply the degree of the irreducible polynomial of alpha, which is f. So this is going to be my cubic irreducible polynomial. So claim is k is equal to the splitting field of f over capital F. This proves the problem, right? So this solves the problem. Why does it solve the problem? This solves the problem because I am asked to show that k is a splitting field of an irreducible cubic polynomial. It is a cubic polynomial. Cubic means degree 3, of course. It is irreducible by choice because it is the irreducible polynomial of an element. So if I show that k is a splitting field, I am done. Okay. So why is this? So the proof of the claim. So let me, it's very easy to prove this claim. And it is where in this proof we are going to use that kh is not Galois over f. So first point to note is k splits completely, sorry, f splits completely in kx. Why is this? Reason for this statement, why? Note that k over f is normal because it's given to be Galois. It's important that I take a Galois extension. So it is a normal extension and f is a polynomial over the base field, has a root alpha in k. So alpha is in f alpha, of course f alpha is contained in k. So it has a root in k. So one of the equivalent characterizations of normal extensions is that any polynomial, irreducible polynomial, f is irreducible also. Any irreducible polynomial which has one root splits completely. So that proves the first statement. So let alpha 1, which is of course alpha, alpha 2, alpha 3 be the roots of f in k. Because it splits completely, remember there are 3 distinct roots also. Because it's a normal Galois extension, it is separable. So there are 3 distinct roots. So call them alpha 1, alpha 2, alpha 3. So note that f is separable. So rather I will say alpha in k is separable over f. So f has distinct roots, being the irreducible polynomial of a separable element. So the second statement that will solve the problem is k equals f alpha 1, alpha 2, alpha 3. Remember, a splitting field is not just a field where the polynomial splits completely. In addition, it must be generated by the roots, because you can take a bigger field, it will not be a splitting field. So here I am claiming that it is the splitting field. I am not merely claiming that a cubic irreducible polynomial splits in it. I am trying to show that it is in fact generated by the roots. So let us look at where this can fit in our picture. So this is our picture. What we know is that this is degree 3 and this is degree 6 because its Galois group is S3. So hence its degree is 6. So remember, of course, we do know that the order of the Galois group is the degree of the field extension because, and this is 6, and because this is S3, this is 6, and this equality is because K over F is Galois, right? So it is a degree 6 extension. I should have mentioned that before. So this is degree 6, this is degree 2. So that means K colon F alpha 1 is 2, right? So maybe let me write that. So this is 6, this is 2. So now F alpha 1, alpha 2, alpha 3 is an intermediate field of a degree 2 extension. So this implies K equals F alpha 1, alpha 2, alpha 3, or F alpha 1 equals F alpha 1, alpha 2, alpha 3, right? Because this is a degree 2 extension, these two numbers multiply to 2, that means you can either have this is 2, this is 1, in which case this happens, or this is 2 and this is 1, in which case this happens. So we are trying to show that this happens and that this doesn't happen. And we are done now, right? Think about it. Why doesn't it happen? Because if F alpha 1 equals F alpha 1, alpha 2, alpha 3, then this of course is Galois, being the splitting field of a separable polynomial. So this implies F alpha 1 over F is Galois. This is exactly what I said is not the case, right? So this is not Galois. This of course is F alpha. So if F alpha over F is Galois, the corresponding subgroup will be normal, but we know that in order to subgroup of S3 is not normal. So this is not Galois. So this is wrong. So if this happens, we get a contradiction. So hence K equals and K is the splitting field of F as required. So we did produce a irreducible cubic polynomial. F is irreducible cubic polynomial whose splitting field is exactly K, okay, which is what I am trying to show. K is the splitting field of an irreducible cubic polynomial, and we showed that here. Okay, so let me stop this video here with this problem, and we have a few more problems that I want to do which apply main theorem of Galois theory. Thank you.